So let's do something completely different. And let's talk about how to cast a small engine block or any other part that you want out of aluminum. Now this one is heavily flawed. It has some damage. Yeah, that's for good cooling. Yeah, so this one is definitely flawed, but this was actually my very first aluminum casting ever. And being my very first aluminum casting, I'm kind of proud of the way that turned out. Now I have no desire, or when I did this, I had no desire to actually try to make this run, because that's a massive project to do that. I do know people who could do that. And maybe you're out there watching thinking that you could do that. It is possible. Not this one, because it'll leak oil all over the place. But I just thought it'd be cool to have a little engine block as a paperweight on my desk at work. But I want to go ahead and talk about how I did this. For many years, I've been wanting to do aluminum casting. And last year, which is before I started doing YouTube videos, so I apologize, I'm not going to have step-by-step instructions on how I built the equipment, but I will show you the equipment and I'll talk about how I built it to give you some ideas on how you can build your own. And at a future date, I will go through, I'll do a video and actually make something else. Right now, I don't have anything else to make. I'm not working on any projects that need a casted part. So I don't plan on casting a part soon. But the next time I do, I'll make sure I do a video of that process. So this will just be kind of a an introduction to the equipment that I made, what it is, what it looks like, how I made it, so that when I do put a video out on doing this, I won't have to explain all of that as I'm doing that video, because that would probably make that video way too long. And I'm hoping that this one won't be way too long. So for those of you who are not familiar, this is a method called lost wax casting. Technically, this would be lost PLA casting because it started off as a 3D printed part out of PLA. And if you look closely, I don't know if the video is going to show it very not, but you can actually see the layers from the 3D printing. All right, that's how much detail you can actually get out of this. All right, so I want to talk about the whole process of lost wax or lost PLA casting. Talk about what's needed to do that, and also some problems that people have. I see people trying this online all the time, and it just, I mean, yeah, mine's not perfect, right? I know what I did wrong, and I'll talk about what I did wrong and why it did that. There's a good reason why it did that. But a lot of people really make major mistakes, and parts just don't come out very well at all. And I am fortunate to have help. There's a guy who lives maybe 10 minutes from my house, and I found his YouTube channel. He's A1 Marine. So do a search for A1 Marine. He does a lot of lost wax, lost PLA casting. Excellent videos. Again, he's right near my house. I've gone over there a couple of times. He's actually the one who told me why it did that, because I couldn't figure out why it did that, and he told me what I did wrong. So I'll share that with you. So for lost wax casting, first thing you need is a part out of either wax or a 3D printed part. Now 3D printed, easy enough if you have a 3D printer. For wax, wax is going to take more steps, because for wax you're going to need a pattern that you need molded. And let's say, let's say that I didn't have a 3D printer and I needed to do this out of wax. I would have to first make the part out of something else, like carve it out of wood, carve it out of plastic, machine it or something. And then I would have to make a silicon mold, which this would be very difficult with all of the internal cavities and internal parts. It would be very difficult to do this, in my opinion. I'm sure somebody knows how. You would have to make a silicon mold of that and then remove the original part, and now in that silicon mold inject that with wax. And then when the wax cools, you'll have the part that in wax that will then be lost. And so anyway, so you take the part. I'm going to draw some pictures here since I have my paper and marker out from the last video. You have the part in PLA or wax, and again, I'm just going to say that's my engine block. And you have to then attach, or if you're printing, maybe you can print it with a like a runner or a sprue, whatever you want to call it. You have to attach something, not like that, I already screwed up. Attach something like that, okay? And then that goes inside of a rubber base, so I can actually use that. There's a rubber sprue base. Side view profile looks something like this. Then over the top of that, you put a metal flask. The metal flask goes around it. The metal flask has a shoulder or a ring around it this way. The metal flask has a whole bunch of holes in it, okay? And then you fill that up with an investment. Now, some people try to use plaster. Plaster is not the best thing to use. Now, first of all, this flask has a whole bunch of holes in it. In fact, give me 2 seconds, I'll show you a couple. Okay, let me show you what some of these parts look like. This piece right here, that piece right there, it's this. This one I actually 3D printed. I 3D printed it out of Ninja Flex, okay? And so the sprue here goes in right here, like that. That holds the part in place. This lip, I know it's dark, so it's kind of hard to tell. That lip here has a little bit of a ridge around it to help hold onto the flask better. Now the flask I used, now this is going to look ugly. You ready? Yeah, look at that. I've never cleaned out the old investment yet. That's left over from a while ago from when I made this. So this actually came out of there, okay, like that. So with the PLA part suspended on that base this way, and you can actually see the polished areas here. That's where I had it attached to the runner. And I don't know if runner or sprue is a correct technical term, but that's where I had it attached there. And then that all went right over top of this, like that. And pieces are crumbling out. I'm making a huge mess. I made this out of just, ew, there's spiders on there. I made this out of steel, and I got some pipe, drilled some holes in it, put a cross piece here, put the flange on it, and so then the engine was like setting down inside of here, the plastic one, all right? And since there's holes in it, I had to wrap the whole thing around with tape. Then I mixed up the investment, and there's a few different kinds of investment. Again, a lot of people try to use plaster. And yeah, that looks like plaster, but it's not plaster. Don't use plaster. If you use plaster, you're going to get some bad results, okay? The investment I use, little spider, the investment I use is designed for lost wax casting. And I've got a box of it under my counter. I'll have to get a name for you here in a little bit. I don't remember off the top of my head the name of the stuff, but there are a couple of different manufacturers, a couple of different products. And the thing is, the stuff I get, it's cheaper than plastic. Pound per pound, it's cheap. I said plastic, plaster. It's cheaper than plaster. So people use plaster because they think it's cheaper, and it's definitely easier available because you can just go right down to your local wherever and buy it. But pound for pound, even with shipping, it was a few cents less than plaster, okay? So once this investment is set, and there are very specific rules for how long it takes for it to cure and set and mix it. You have to put it in a vacuum chamber before you pour it. You have to vacuum out all the bubbles, okay? So you have to run it through a vacuum setup, which I had to build my own vacuum setup. So it's a several step process, but I mean, once you actually start getting into it and doing it, it's really not too bad, all right? So now you've got the plastic part in there. The investment is all set up and cured. You then take this piece off, okay? You take that piece off, which will leave, you'll see where that little sprue is sticking out, and then you put this whole thing in an oven. Don't use your kitchen oven. I mean, I guess that would work, but you know, you really got to get up to 1,000 degrees, so yeah, don't use your kitchen oven. So I had to build what's called a burnout oven. The burnout oven burns out the PLA or the wax. You get it up to about 1,000 degrees and it'll burn all that out, okay? Now it's, again, you have to step it up. So you bring it up to say 300, let it set there for a few hours, bring it up to like 600 or 800, let it set there for a few hours, and then bring it up to about 1,000 to 1,200 and let it set there for several hours. and then let it cool back down to about 500 and let it set at 500 until you're ready to pour. Okay, so yeah, I'm glad I have this paper towel down because I'm making a huge mess. Okay, so now after that burnout, what you have is this flask again, and there's a ridge around it for a reason. You have that flask with an open cavity of your part. And then you have to pour in aluminum, which obviously it has to be this way to pour in the aluminum. Now, the reason why the type of investment you use is critical is because of the temperatures involved. Like I said, this whole thing's in an oven at 1,000 degrees or more just to burn out the wax or the PLA. And PLA burns out just as cleanly as the wax does. If you use plaster, okay, it will probably crack. Also, let me draw the walls in here of the flask. And there's holes, right? I showed you the holes in there. The material here, the investment material, is slightly porous. This is important because when you pour in the aluminum, you put this in a vacuum pot. That's why there's a flange around here. Okay? So you have a vacuum pot. There's a line in here that goes out to a vacuum pump. P is for pump. So this whole thing is under a vacuum. Since this material here is porous, as you're pouring in your molten aluminum, okay, the vacuum is sucking all of the air out, which sucks the aluminum into every little nook and cranny and crevice of that open cavity. That is why you can get such fine detail as the actual print lines left over from the 3D printer. Okay, so that's how the whole process works. So obviously you need a burnout oven to burn out the wax or the PLA. You need a kiln to melt the aluminum. You need a vacuum pump. You need a vacuum pot, and you need a flask. Okay, and you need crucible tongs and a crucible. Do not use a cut off bottom of a steel fire extinguisher and then a pair of salad tongs. Okay, the cut off bottom of a fire extinguisher, yeah, it's okay for a couple of uses. I mean, it's steel, aluminum melts at a lower temperature than steel. Yeah, that's fine, whatever. But I saw somebody on YouTube, I'm not going to mention his name because you guys are if you're watching me, I know you've watched him. He's a very popular YouTuber. But he uses a pair of salad tongs to remove the crucible and pour the molten aluminum out with salad tongs. You're just asking for problems. And he's gotten away with it so far, but yeah, he's just asking for problems. Let me show you another flask that I got. Now this one I did not make, obviously. I bought this one. And this one is stainless steel. Again, it's got the holes for the vacuum assist, the flange that makes a seat on the top of the vacuum chamber. This one gives me a much bigger area, a larger area. And this is only like 45 bucks. Okay. Now, this one, I went to my local steel shop. I don't have a way of welding stainless steel yet, so this is just normal steel. I would love to make these out of stainless, but I just can't. I don't have the equipment to weld stainless at this point. Maybe someday I will, but right now I don't. So, and then I painted it with like a high tip paint. It was rated for like 1200 Fahrenheit. Yeah, I still cooked all that off. Let me show you real quick. Let me show you the vacuum pot. Okay, this is the vacuum pot that I made. And it has the fitting here for a vacuum hose. I welded a bottom plate. It's basically just a large piece of pipe. Welded a base plate on it. Welded a top ring on it. I glued on a seal. I bought that online. It was like, I don't know, 10 bucks or something. And I made this specifically to fit this one right here. And that'll make a nice tight vacuum seal when you put the vacuum pump on. Now, if I use the other flask that I bought, it's tall enough, but as you can see, I wasn't thinking very clearly when I designed this, because this one, that flange is a lot smaller than the flange on the one I made. So I'm going to have to make an adapter plate to fit under here. with another seal. Okay, so before I can actually use this one, I'll have to make some way to adapt that on there, which shouldn't be that big of a deal. But here's the thing, when you make your own stuff, you can save a ton of money. I got enough material to build this vacuum pot and 2 flasks. I only built one, but I have enough material to build another one. And all of that cost me was maybe like 15 or 20 bucks. There's no way you can buy one already made for, I mean, even twice that. There's no way. It's just way too expensive if you buy this stuff. So if you have some way of cutting metal and welding metal, even if you just know somebody who can cut or weld, you're still going to be dollars ahead if you make it yourself. And anyway, so let's hopefully this is all making sense. You know, if you have any questions, please feel free and put it in the comments and ask some questions. And again, later on, someday in the future, when I actually use this, hopefully it'll make even more sense. But again, this connects to a vacuum pump. That's this piece right here. So as you pour in your molten aluminum, the vacuum sucks all the air out and then sucks the aluminum in to fill all the cavities and crevices of the mold. And then once it's once it's cooled, once the aluminum is hardened, you just take that thing out and plop it in a bucket of water, and the investment material will just break apart. Okay, it'll just completely break up and break apart, and then your part comes out. There is a little bit of cleanup. You know, you take like a little wire brush or something, and you just kind of wire brush any investment that's still left in there. Now, the reason why this one failed, the reason why I have some voids in here, let me get some of this stuff out of the way here, and I'll show you exactly what happened. When you pour the aluminum, you would think that you want this to be the same temperature as the aluminum, because you would think if this was cold, as soon as the aluminum hit, it would solidify. Well, that's not what you want. You want this to be approximately 300 to 500 degrees. You don't want it any hotter than 500 degrees. When I poured my aluminum, this was probably about 800 degrees, okay? And notice that this is right in the middle of the flask. That's the hottest part of the flask, okay? So what happened was, when I poured all of the aluminum in, when this was all full of aluminum, this was the hottest part, so this cooled down the slowest, okay? This up here cooled down first. So that cooled down, and when molten aluminum cools down, it shrinks. And when that cooled down and started shrinking, it had to pull aluminum from somewhere. So it started sucking aluminum up this way, which sucked aluminum out of here, which is what created these voids in here, because it started sucking aluminum out of this. So if this is about 300 degrees when you pour, it will start cooling down sooner than it did. But by pouring with this at 800 degrees, and it might have even been warmer than 800, that kept that molten for way too long. Ideally, you want this to cool down first, so as it shrinks, it pulls aluminum from here. So what I should have done, I've got a mess to clean up now. What I should have done is, in the flask, say this is the flask, I should have had, like, say, the engine block maybe over here, like lower and off to the side, and have the sprue runner come down this way and then attach to it like this. So as this cooled, it had all of this material to suck aluminum into as this cooled. That would have worked much better. But this is one of those things that you just kind of learn from trial and error, okay? Your first time doing this is probably not going to turn out very well, unless you get really lucky or you do more research than I did, okay? So let me show you some of the other equipment. I'll show you the kiln and the burnout oven and a few other things. So let me show you some of that stuff. Okay, so this is what I use to melt the aluminum. And if it looks familiar, well, that's because it might be. It's used to be a bread maker. Now you'll notice the burn mark here lines up pretty good with the burn mark here. That's because I greatly underestimated how hot 13 degrees is. And the first time I powered this thing up, it got away from me. I think it actually got up to about 2200, I think, because the digital readout here, that stops at like 2200, and it was just all like, yeah, it was at its limit. And that was like turning brown very quickly. So I shut it off, shut it down, unplugged it. And actually what happened was, as it was getting hot, as it was heating, I have a solid state relay in here that connects power to the heating elements inside of here. The heat actually melted that relay, so it was stuck on full blast, and I didn't realize it. And then the temperature just like really got away from me. So by the time I noticed that was scorching and I turned it off, it was too late. Everything in this side was fried, so I had to completely rebuild everything in here. And but anyways, what I have in here, this is a MyPin TA6 digital controller. I have a switch here. This is main power for the whole unit. I have a switch here that I can turn the fan on and off with. I got a nice big cooling fan back here. Now right now, see, this temp controller has two outputs. One output turns the heating element on and off to a set temperature that I put in here. The other output turns the fan on once it just kind of gets up to, say, 70 or 80 degrees. That way the fan doesn't just come on as soon as I turn on the unit. It comes on after it's been on for a little bit of time. I have another toggle switch here where I can just directly turn off the power to the heating element. So if I need to just shut it down for whatever reason, I can just turn that off, which will leave the cooling fan on to cool the electronics, but I can turn off the heating elements. This is a little bit of overkill. I mean, really don't even need all of this. If all you're doing is melting metal, you know, you could just plug it in and let it heat up until your metal's melted and be done with it, and you don't need all of this stuff. But I wanted a little bit of control, which, yeah, I probably shouldn't have done all that, but whatever, it's fine. Now this panel here, I bent that up out of steel because this was on the original bread maker. This was all plastic. This part here is still plastic, but the heat doesn't get over that far. So I didn't want it melting here. And again, remember when I did this, this was all the way up against that. So that's why that was metal. If I knew I was going to split it apart. So once I realized it got too hot, I basically just ran the whole thing through my bandsaw, cut it in half. I had to build a new wall in here, build a new wall here, and put some spacers in here to separate it. So it's not as pretty as I wanted it when I first made it. Oops, sorry about that. It's not as nice looking as I wanted, but it's definitely more functional. These pads in here, this is a ceramic wool blanket. I probably don't even need those in there, but they're there because I don't really have anywhere else to put it. The heating elements inside here. And again, the lid, this part of the lid was original to the bread maker, but the outside of the original bread maker is plastic. So I cut all that off, and I took a piece of steel and cut it to shape, bended it over, welded all the seams, and just kind of pop riveted it on there. And put some insulation pad. This is wood burning stove door seal here. And again, the white in here is ceramic insulation pad. There's my crucible. Let me just pull that out of here real quick. That is setting on a graphite block. And down there in the far corner, right down in there, you can see the temperature probe that reports the temperature back to the digital controller. And the heating elements, I ordered those online. I found a website. I'll have to show you a sticker later. It's Euclids, EUCLIDS, something like that. They specialize in heating elements. Now I could have just bought the nichrome wire and wound it myself, which is what I did when I built my vacuum forming machine. That's another video I need to make one of these days, is my vacuum forming machine. And I wound the coils for that, but that only has to get hot enough to make plastic a little bit soft. I didn't have to melt aluminum. So to make sure that I had a coil that could handle and get up to temperatures to melt aluminum, I decided to leave that up to the professionals, the people who do that all the time for a living. So I gave them I emailed them. I told them the dimensions of the box. I told them what temperature I needed to go up to. I told them I only had like a 110 outlet. It's actually a 120, but whatever. And they custom made the coil for me, sent it to me. It was like 45 bucks for that coil, maybe 47. And I just went through here with some stainless hardware, and they go through ceramic isolator blocks. You can get those on eBay. There's probably a few other websites you can get them. And that goes through. I have 3 separate wires here. This is a high temp sheathing that I got on eBay. I think it's capable of handling like 1200 or 800 or something like that. But one heating element wire through each one, and then the wire for the temp sensor through that, then through here to the electronics. I almost knocked my crucible off. This is an A7, I think, salamander. I forget. Put that back in here before I knock it off and break it. That would suck to break it after only using it one time. All right, so this is how I melt the aluminum. Again, I did this way before I started making YouTube videos, so I apologize I don't have a step-by-step. If I were to do another one, I would not use a bread maker. I would custom make a steel enclosure for the job. I mean, this works, but, you know, it didn't really turn out the way I had envisioned it. And I also have, I didn't mention it, but I have about 2 inches of this ceramic pad in here, all the way down underneath and all the way around. But when that gets up to aluminum melting temperature, that still gets really, really hot. You can't touch that. And one concern I have with this is when I first started doing it, I assumed the steel liner here was stainless. It is not. So after a few uses, I don't know how many, maybe 2 or 3, or it could be 30 or 40 uses, that steel liner wall will probably start to fail. So eventually I will remake this with a thicker stainless, and it will be purpose built. So anyways, if this gives you any ideas for how to make your own, I made the hinge for the lid so it stops about halfway up. And but if that gives you any ideas on how to make yours, that's great. You know, feel free to steal my ideas. I'm joking. Let me show you the burnout oven. So since I used a bread maker for the kiln, I decided to use a microwave for the burnout oven. Now, for the burnout oven, I'm still using a TA6 controller. It's really dark over here. And now for this one, the controller is definitely necessary. And I have the cooling fan over there. Just behind the cooling fan is a digital relay for the temperature. Because remember, with this one, you have to bring it up to 300, let it set for a few hours, bring it up to 600 or 800, let it set, and bring it up to 1,000 to 1,200. Now, they do make temperature controllers with a ramp and soak time cycles, but those are really expensive. So I'm just doing all the timing myself. I'm just ramping and timing my own instead of programming something to do the ramp and timing for me. To open the door, shut down, door comes open, and there we can see inside. Again, I have that ceramic wool insulation inside of the door, and I have more inside of the oven. There's my heating element coils that look all nasty. And it's the same coil as we just saw in the forge. Now, I had some problems. That little insulator block, I had it tied in there with steel wire, and the steel wire actually melted and broke, so that's sagging down quite a bit. I used stainless steel wire. I'm going to redo that with this stuff, nichrome wire. This is a thicker diameter than the stainless steel wire I used, and it can handle higher temperatures. So some of those wires that hold the ceramic loops in broke. So I'm going to have to redo some of those. And here's some of those insulators, those little ceramic donut insulators. Again, you can get them online. The heating element came from these guys right here. So you can see their website, their company. Again, you just go onto their website. They're very helpful. They know what they're doing. Give them the specs that you want, and they can make and send you a heating element. Again, these were like 45 bucks each, and they work incredibly well. So again, you know, like I said, I used a microwave for this. It worked. It's fine. But again, if I had it to do over, I would just custom build an enclosure instead of repurposing something else. I think it just would have been a little bit better. But again, feel free to use any of these ideas that you want. Also, like I said, don't do what that one guy did and use salad tongs to get your crucible out. You need a set of crucible tongs. That's what I made right here. So this, let me just get this where we can see it better. Okay, let me come over here. This will go down, grab the crucible, and you can see the handle here. That handle, I can open and close it. So I can push those apart to open the tongs to go around the crucible, and then squeeze the handle, and that will then close that around the crucible. I can then lift it out, and with this tool, you just set it down here, get a wider view of it, okay? So with that one tool right there, I can lift it out of the forge and pour with that one tool. I see a lot of people online, which now this is standard, I'm not faulting anybody, but usually what happens is they'll use one tool to lift the crucible out, then they'll put that in a pour tool, and then they'll pour. I wanted one tool to do everything. I figure the less I'm moving that thing around between tools, the less or the better chance I have of, you know, not spilling and making a mess. Okay, that was just solid steel bar that I hammered to shape, cold. You know, I didn't have a torch to heat it up. I just it took a while, and I was welling on those things to get those bends in. Yeah, I think I actually used this. I held it on the edge of that, and I was just welling on it with my largest hammer to bend those over. Drilled and tapped for a threaded rod. I have two fiber lock nuts, so I can adjust how far it opens and how far it closes. So this is the most it'll close, so I won't crush my crucible. If I get a smaller crucible, I'll have to adjust that. If I get a bigger crucible, then I can adjust that so it won't close as much. So I can turn those in to adjust how far it opens and closes. And this works incredibly well. I'm so pleased with this. Don't judge my welding. You know, you can look at this one. Don't look at that one. Yeah, don't look at that. It works. It holds. I'm very pleased with this one. Okay. So we also need a vacuum setup. I'm not going to drag that out of there, but it's just a vacuum pump I put on a wooden support, and that piece of PVC here makes like a vacuum tank. So, and of course I've got a vacuum gauge, some hoses, some shut-off valves, and I've got a vacuum switch here that will turn it on and off at the vacuum that I tell it that I want it to make. So anyways, man, I keep putting my finger in front of the lens. So for this whole setup, okay, the vacuum pump, the burnout oven, the forge, the crucible, all of this total probably cost me a couple $100. Whereas if you bought just, say, if you bought an already made forge, an already made burnout oven, you know, you can't touch those for less than $400 or $500. And I've got everything for a few hundred, like no more than $300 for everything. So the more you can make on your own, you know, you might have to mess around with it a bit. You might have to tweak it a bit. You might have failures like I did here and have to rebuild stuff. But it's more rewarding, and the money you save is just astronomical. If I had to buy everything, I couldn't have afforded to do it. Okay. And before I leave you here, let me just show you the schematic that I used for the burnout oven in the forge. I almost forgot. This is the investment material to use. Again, there's a couple of different ones. This is one I'm using. It's Ransom and Randolph Plasticast, and I think it's a 40-pound box. It's kind of dark under there. It's under my bench. But do a search for that. Order that. That's what you need to use. Do not use plaster, because like I said, pound for pound, this is actually cheaper than plaster. So use the right stuff. All right, let's look at the circuitry that I used, again, for the burnout oven in the forge. Not the best drawn diagram, but it'll work. Here's the plug. Now, One thing I did not draw here, but definitely do not put this on. Make sure it's a 3-wire plug, and 1 wire goes to a ground to the chassis of the box that you're putting your heating element in. Okay. The hot through a bank of fuses. I have 1 fuse for main power. It'd be like a 1 amp fuse. Goes to the main power switch, which goes to the PID controller. My pin is a T6 controller, the digital controller. I have, now I show 2 fuses, but I only used 1. 1 fuse through the heating element switch that goes through one side of the digital relay that then goes to the heating element. I'm not sure why I drew 2. It looks like I have 2 10 amps, but instead I just use 1 20 amp fuse. So yeah, just 1 fuse is good enough. And then 1 fuse through the switch for the fan. Now notice I made a change to my diagram here. With this setup, the fan was always on, controlled by the switch here. I broke into the wire and I had that come to another output from a relay of the controller. Because remember I said the controller has 2 outputs. So I programmed the controller to turn the fan on after the inside of the box got up to about 80 degrees or so. Okay. Now the fan is there to cool the digital relay because that starts getting warm after it's been on for a while. So the fan is there to cool the relay. But I didn't figure I needed it on until it actually started working a bit. So by the time that gets up to about 80 degrees, the fan turns on. That way it's not running the entire time the box is plugged in. Even though I do have a switch to turn it off with. Still, whatever, you could do it either way. The main reason I did it is because I had an output here. I figured I might as well take advantage of it. Okay. There's your temp controller, measuring the temperature inside of the box, going to the PID controller wired to the digital relay that then completes the circuit for the heating element. From the common side of the plug, I just have a junction block here. One goes to the heating element, and one is the other power side from the temp controller. That's a nice thing about these. They run off of 110 or 120. You don't have to, drop it down to 12 volts or whatever. It's you've got 24 volts, I think that's right, 24 volts out to here, DC, and but it just runs off of your main power. And the fan also ties into the junction block here. All right. Now another one here. Remember the switches I used were lit switches. I don't know if you saw that, but on each of the switches was a tiny little red LED, an indicator light. That's what the 3rd wire here is for the indication. Okay. And if you don't have to use indicator switches, you could just use normal on-off switches. It's perfectly fine. But one of those is for the indicator part of the switch. Otherwise, you can just ignore that. Now you notice there's a lot of little tick marks here. What I did was, as I was wiring it up, I would put a tick mark on each connection so I would know. That's how I kept track of when each connection was done. All right. I know this is really messy, but I hope it makes sense. Now, as far as the cooling goes, I just drew a little diagram here. Again, there's the fan on the side of the box. The fan is cooling the digital relay. I have a wall here as a heat break. There's a hole in the wall, so cooling air can go across the relay through that hole in the wall and out the back. Then I have a 2-inch air gap. Actually, yeah, 2-inch air gap, and then the insulation, the fiber mat insulation out here. Actually, I have more like a 3 or 4-inch air gap. But anyways, that's just kind of how I wanted the fan to blow and cool the electronics. And trust me, if you get that too close to your heat box, and if you don't have enough insulation, that will melt. I guarantee it. That kind of sucked. That was a bad day. I was not happy. But anyways, it's fairly simple, fairly straightforward, but this is all it is. Okay. So anyways, like I said, one of these days I will do another casting. And when I do that casting, I will do a video of that, and I will, you'll see step by step the whole process. And but as I do that, I won't have to explain any of this again. Okay, this is kind of like a precursor, or yeah, you get what I'm trying to tell you. So I'm going to leave this alone because it's probably getting to be way too long. But I hope this was helpful. I hope you enjoyed it. I hope you learned something. And again, check out A1 Marine, his YouTube channel. He does a lot of cool stuff. And if you have any questions, don't hesitate to put a comment. I read all comments, and I do pretty well with replying back to comments as needed. So anyways, as always, thanks for watching.